Very well. Now, let's take our result, our fundamental result for the total force on some wire, right? And let's do an example. Let's compute the force then on a rectangular loop where the sides of my loop are made out of wires that are carrying a current. So then here's the situation for the example I hope to compute. So I'm going to have a wire moving over here to the right, carrying a current I1, and I have to have it oriented towards with the current flowing to the right, because right now this is the only magnetic field that we actually the only situation for which we actually know the magnetic field. Then above it, I'm going to have this rectangular loop. So the loop will look something like this. Here, it's got a certain length to it, and it extends between two certain distances from my wire. The current I will have flowing here this way, clockwise around my rectangular loop, like so. And I'll set this up somehow with some kind of a battery and a resistor or something. And I will ensure then that it has a certain current flowing, which will have the magnitude, the value I2. The other parameters in the problem here then are going to be, again, like I said, the length of my loop here will be L, and it's going to extend between two different distances from my wire. The first distance here will be R1, and I'm sorry that my diagram came out a little poorly. It's supposed to be parallel to my wire here, so I will just emphasize that. This is also R1, despite what the figure seems to be indicating. And then finally, the upper distance to my loop, that I will call a distance R2. Now, my job then is to calculate the total force on this loop. The magnetic field, just to remind ourselves that we know, our famous result for a wire like this, is that the magnetic field is minus mu naught I divided by 2 pi r times k hat, where k hat is the out of page direction, so we should have our coordinates here also on our diagram. This is the I hat direction, is to the right, j hat direction is up, and the k hat direction is then out of the page. So, our job, compute the total force on this loop. The way we do this, of course, is following our prescription up above. We have to integrate over the entire loop this particular integral. So we have to integrate all the way around here like so. So much like we do with our Gaussian surfaces, our strategy, of course, is going to be to break up the total integral around the entire loop into a series of components, one in this case for each of the four sides of my rectangle. So it's going to be useful for me to actually label these sides right now before I begin. So I will call this here side A. This one here will be side B. This one here will be side. Oh, I want to make the top one C. Probably be a little more orderly. I'll just go in alphabetical order. This will be A. This here will be B, C, and this one here then will be D. So let's begin with these then, one at a time, and I'll start with A. So FA. So for FA, the job then is to integrate here along this pathway. So that's going to be then, let me slide up a little bit as we compute. That's going to be then the integral along A. The basic formula, sorry for going up and down a little bit, for that force then is I dl cross B. So that's going to be I times my dl vector crossed with my magnetic field. In this case, notice the magnetic field I'm dealing with is always at the same distance r, so it's going to end up being a constant value. That will be useful for us, but this is the magnetic field at location or distance r1. Now, to do such integrals, particularly the first few times we do them, and I recommend doing this always, that's always my expert tip, is to very carefully break out first any vector products. In this case, it's a cross product, something a little bit new for us, so we're going to go through this one very slowly and carefully. So what do I have? I have the integral then, right, over side A. And as I integrate over side A, I have my factor of the current I. And we should be very careful now about our various currents. This formula, the current I here, refers to the current flowing through the particular chunk that you are considering. In this case, we're talking about the current flowing along the side here. And notice that the current flowing along the side, and actually all the way around this loop, is I2. So I should be very careful here to make sure I always include the proper current and the proper location. So I've got current I2. Back to my cross product. I know the magnitude of the cross product will be then the magnitude of each of the vectors, dl, times the magnitude of b at r1. That's nice. Times the sine of the angle between them. Now in this case, my dl vector, of course, is pointing off to the right. As I perform this integral, what I'm doing clearly is breaking my wire into a series of chunks, right, that move off to the right like this. So this is what dl looks like. The magnetic field, remember, is straight into the board. It's in the minus k hat direction. So here I'll draw a little sketch here. It's always inwards, so it just gives me an idea of the general direction. Now, the angle between the vector going off to the right and the vector that's going straight down into the page, well, that is clearly a right angle. So that will be the sine of 90 degrees. And fortunately for us, we happen to know the sine of 90 degrees. That's just a value of 1. Finally, we have to include the direction of our cross product. And this is where we will be breaking out our right-hand rule. But now let's see here. I have my fingers should orient themselves along this leftward direction, right? So if you take your right hand, you can't see this on the screen, but if I take my right hand with my fingers oriented in that direction, then my job is to rotate my wrist around until I find a way where it's easy for me to curl my fingers in the direction of the second vector, which is the magnetic field, which means straight into the page. And what you'll realize is, well, you want your fingers pointing to the left and your palm pointing down. Then it's easy to curl your fingers down towards the magnetic field. Then you just stick out your thumb, and that tells you the direction of the cross product in this case is straight down on the page. So the force here, if I can draw it then, on each of my little vectors, and therefore also, because it's in the same direction for the entire side, the force on A is actually going to be in this downward direction. Or, mathematically, that's the minus j hat direction. And this should, by the way, come out fairly intuitive for us, because after all, if you think about it, these are two parallel wires with currents flowing in the same direction. And we've already seen it's kind of the opposite of charges. So we have like currents. Those actually should attract each other, the opposite of what charges do. And indeed, we are seeing that this is a downward force. It's an attractive force. So the direction actually makes a lot of sense to us. Okay, good. So now we're getting somewhere. We can continue here and simplify. The magnetic field, its magnitude, we actually know. That comes to us here from above. That's just mu naught times I over 2 pi times the relevant distance. In this case, we are always at distance r1. So that's a very nice result for us because that's going to be constant. The current density is constant. So also, by the way, this vector is constant, so you can factor it out of the integral if you want, or just realize all the contributions are in the same direction, downward, so I'm just computing really the downward component here. Either way you want to think about that, I can factor out then my I2. I can factor out my magnetic field. Ooh, but we better be careful. Notice this I didn't include the proper subscript. Magnetic field, this is a generic formula for magnetic field. we have to remember this is the magnetic field coming from somewhere. This magnetic field is coming from the flow of this current I1. So actually, in this case, the magnetic field has this factor of I1 in it. So that's my I1. So when I pull out my constants, I've got I2 feeling the force and I1 creating the magnetic field. So I've got another factor then that comes out, mu naught I1 divided by 2 pi R1. Now, I've included, of course, my sine of 90. Okay, there's a minus j hat direction. I've included all of these factors. The only thing that's left then is the integral over A of the magnitude of dl, and the whole thing then is in the minus j hat direction. All right, now I think we can handle this here pretty well, right? Because all that's left in the integral is just to add up the lengths of all of my little displacement vectors. Well, my little displacement vectors carry me all the way across this wire, so it's just the length of this wire. So at the end of the day, what I'm left with then is just the following series of factors. I've got mu naught, this integral here, as I said, just becomes the length, which we had specified actually was L. So what I end up with then is a couple of ways of looking at this. I get I2, right, times the magnitude of B. That's what this quantity was, times the length L in the minus j hat direction. Or if I want to write it out in terms of all of the given variables in the problem, I've got a factor of mu naught, both factors of I, that goes on top. So I have mu naught I1, I2 go on top. Then it's divided by 2 pi times the distance between those two wires, which was just R1. There's then also a final overall factor of length and a direction minus j hat. So that then is the total force on side A. Would look like this. Now, there's a very important lesson that I want to draw out of this calculation that will make these types of questions easier to answer in the future. Something very nice happened here, of course, and that was that the magnetic field was just constant over this wire, right? So that makes things a lot easier. And so it's good for us to keep in mind what happens. So when the magnetic field B is constant and the wire is straight, that also made things a little bit easier for us. Straight. Then in those conditions, the force that you get is just the current that's flowing times the magnetic field times the length, and then you can get the direction very quickly from just doing the direction, right? This IDL factor, which is the direction of the flow of the current, and doing the cross product with the magnetic field, which is exactly what we had done. So that's just a quick handy fact when the magnetic field is constant. Okay, so now let's now proceed to the other three sides of the wire.